Okay, hello. Welcome to this problem. So today we're going to be solving this problem about a puppy and a remote control car. So when we first look at this problem, we're going to notice values with this M and S, 32 meters, and we see a bunch more M and S. So M means meters, S means seconds. We can see this says constant speed and accelerating, as well as uniform rate. So that will basically be a telltale sign to me, at least, that we need to use kinematics to solve this equation, which is what I'm going to be explaining how to do. So you might be asking, what is kinematics? Well, kinematics is the study of motion in physics, and we're going to be focusing on three main things here, which is acceleration, velocity, and time. So I'll start with velocity because I'm pretty sure time is pretty well known. It's just a period of time. But basically, so we can see that we have constant speed, uniform rate. So one of the most important parts of kinematics is that the acceleration is always going to be constant. So yes, so now we're going to look at velocity. So velocity is, or the average velocity is the delta x, which means change in x, x meaning position, so position or distance from starting point, and the time is t, so it's divided by time. So say a dog starts at 3 meters and goes to 4 meters in 1 second. We can say that it's traveled 1 meter, because the change in x is 1, and it's taken 1 second. So that'll give us 1 meter per second as average velocity. So now acceleration is a little bit different. Basically, it's the velocity over time. So velocity was position over time. So it's like position over time again, which is why we can see here we have meters per second squared, which tells us that's an acceleration value, because meters is the position and the times are both in terms of seconds. Time times time is second squared. So now with that out of the way, we are going to be solving for an equation that'll help us find the answer to this question. So I'm going to start with the velocity average. So I'm going to write a bar above the v to represent average. Okay, so now we see this change in x. That's just saying the x initial, or x final, sorry, minus the x initial. I'm going to draw a little circle here to represent initial. That means that's a symbol called a knot, but that represents the initial position. And then we're going to be dividing that by t. So now I'm going to do the same thing over here with acceleration average. So again, I'm going to put a bar above this. This little AVG just means average. This bar also means that it's average. And the thing is, in kinematics, we have constant acceleration, or uniform acceleration. So that means that this acceleration's average is going to basically be the same regardless of what the beginning and end are, because they're the same. So now we're going to look at change in velocity. The delta, again, triangle, means change. So that means it's the final velocity minus the initial velocity. Again, the same symbols, F for final, O means not, and that means initial. And then we're, again, dividing it by t. So now what I'm going to do with these two is I'm going to use algebra to solve for v final and x final, because I want to get those out of here. So when we use algebra, we're going to multiply both sides by t, and we're going to add the VO on the other side after we've done that, giving us a value of v final equals a times t, plus we have the VO moved to the other side by adding it, VO. And I'm going to just add a little tail to this so that you know it's AT. Now I'm going to do the same thing, solving for x final here. So x final equals, again, we're going to multiply velocity by t. This is the average. I've removed the bar here just simply because it doesn't matter where we're looking at the velocity, it's all going to be the same because it's just going to be a flat line. It's all exactly the same versus the velocity will change. The first velocity could be like 1 meter per second, then the next one could be like 5. So we don't really know. So next we're multiplying this by t to get the t out of that side of the equation. And now we're going to add xo, which is the initial x position. So now that we have these two equations, I want to make this even more elaborate. So, because basically saying average velocity doesn't really tell me much, so I'm going to separate that into two components. So average velocity is the same as saying velocity velocity final plus velocity initial divided by 2. It's exactly like as if, let's say, we were taking the average of the number of people in a class, and you take like 5 classes, there's like whatever different numbers, we add them all together and then divide it by the number of things to get an average. So we're just basically doing the reverse of that to get this full thing in here. So now if I put my x of f over here as well, by bringing this entire equation down, this is still going to be multiplied by t, and then we're still going to add xo. So now, if you notice, in this equation, we have a v final, and we also have a v final over there. And what does v final equal? At plus vo, or vo plus at. So what I'm going to do is I'm going to sub this in there. I'm going to place this part into that equation to replace vf, and this will give me an equation that looks like this. So we have x of f on this side. I'm going to make it sub just to make the f smaller so we know it's x, meaning position. xf equals, inside of the parentheses, it's going to get a little bit messy. We have v initial plus acceleration times time. And then we still have our VO on the outside, which is right here. Then we're going to be dividing that by 2. Then we're multiplying it by time. I'm going to make that t just so it's not confusing. And then we still have the xo on the outside. So now we're going to do a little bit of multiplying here. So we're going to just add these two together to get 2VO. And then we're going to divide that by 2, which will just be VO. And then we're going to multiply it by t. So after we factor this out, we get, first off, I'm going to put this over here just to get out of the way, so we don't have to worry about it. xo plus VO times 2, basically 2VO divided by 2 is just V initial, V naught. And then we still have to remember to multiply it by t. And then the last part, acceleration, we're adding that. We have acceleration t over 2 times t. I'm going to write that as 1/2 acceleration times t. And we have to remember that we're multiplying by 2 t's, so it's going to be t squared. And so now this is one of the kinematic equations, and we're going to be using it to solve this problem. So if we move on, we can see the first problem, or in the prompt, if we take a moment to read it, it says AV will have 2 attempts to catch the toy car. Due to her inexperience, the first attempt at biting the toy car is a miss. So it's asking, what is the distance traveled by the toy car from the time AV catches up with it the first time and when AV catches up with it the second time? So we're looking for 2 times. So this might seem a little bit confusing. So I'm going to draw a diagram. So we have, I'll just say P for puppy. This represents AV the puppy. And I'm going to set this as x equals 0. Okay? So we can see this dog is running at 4.85 meters per second. So given it's a constant speed, given it's in the same direction, we can assume that this is going to be the same as velocity as long as we consider the direction of this. This isn't a force, it's just a vector representing the speed. So now it says when AV is at a distance of 32 meters from it, given we're all in the same plane, that can be said as, or explain the same as displacement. So we can just say it's 32 meters from the toy car. Toy car I'll represent with a C. And the toy car begins accelerating at a uniform rate of 0.165 meters per second. That should be squared. So this is going to start moving once this is 32 meters away at 0.165 meters per second squared. So now what we're going to do is we're going to use this handy dandy equation that we derived earlier, and we're going to set up two equations. So I'm going to just write the equation over here. X final equals X initial plus V initial T plus 1/2 A, this is another T, and that's squared. So with this equation, we can set up an equation for each of these things. So I'm going to start by setting up an equation for the dog, which I'll do, how about in red. So I want to find the distance or the position, which is going to be represented by X. We're going to use them interchangeably here, kind of. So the final position of the dog, so I'm going to say X of puppy, P representing puppy, equals, since I've set the reference at X equals 0 for the dog, that means that the initial position of the dog is going to be 0, so I'm not even going to include it in this equation. So I could add a 0 here, but I don't need to. So next, we see plus velocity initial times time. So we know that we have a velocity initial here because in the equations, or in the prompt, it's given by saying constant speed. So what I'm going to do is I'm going to write down 4.85, and then we're multiplying it by t as seen in our equation derived. So we want to know the number of meters we've gone in the number of seconds. So basically, we're multiplying that by number of seconds to get rid of both the seconds, and then we'll know the distance that we've traveled from the position x equals 0. So now it says it's running at a constant speed, so that implies that the speed is not changing, and that means that there's no acceleration, and the acceleration is equal to 0, because if there's acceleration, that means that the speed would increase, because acceleration means that the speed is increasing, versus constant speed just means the speed is remaining the same. So we don't have to include this part in this equation for the x of puppy. So now what I'm going to do is I'm going to do another equation for the x of car. So I'm going to just draw a box around this in blue, a box around here in red, just so we make sure we remember which color equals which. The C also stands for car. So this time we need to look at the initial position. If this is 0 and it starts moving 32 meters away, that means that the initial position is going to be 32 meters. So next we can see velocity initial. So from the prompt, it begins accelerating away once it's at a distance of 32 meters. So that basically means up until that point, it was not moving, so there's no initial velocity, so we don't have to worry about that. So next, we're going to be adding the acceleration. So it's saying it's accelerating at a uniform rate of 0.165 meters per second. And from our equation, we can see that A is fit right in between 1/2 and t squared. So 1/2 times our A, which is 0.165, and then we have our t squared again. So now that we've set these two equations up, what we're going to do is we want to know the distance traveled from the time it catches up the first time and when it catches up the second time. So if we look at this, we can see that this has a square on it, so that should tell us that this is going to be a parabola. So if I graph what this will look like, I'll just draw a little graph over here. If we say this is the position or distance from 0, and this is the time, basically the car will start up at 32, and the position is going to be quadratic, because position, we see the squared, that should be a giveaway that it's going to be quadratic. So next, I'm going to include the dog's velocity. We know that the dog is starting at 0. Sorry, the dog's position. So the dog is starting at 0, but then it's going up at a rate of 4.85. That should be a straight line, but basically it's saying that there's 2 points of collision where it is the same value. So now it's saying, what is the distance traveled by the toy car when AV catches up the first time and the second time? So in between the two. So we have to look at the distance in between these two. Sorry, that's time. Distance in between these two, which would be this. So what we need to find, basically, x1 and x2, and we also have to find a t1 and a t2 to figure that out. So in order to do that, what I notice is that these are the 2 points where the x is the same. So if these are the same, that means these two things are equal to each other. So that's exactly what I'm going to do. I'm going to set them to be equal. So we have 4.85t equals 32 plus, I'm going to just take half of this to make it a little bit less confusing. So half of 0.165 is 0.0825. So plus 0.0825 t squared. And this is a t, so I'm going to add a little tail just to not make it confusing with all the pluses. So now, to make this a real quadratic, we're going to set one side to 0, so I'm going to do that by minusing 4.85t from both sides. So once I do that, we're going to get an equation that looks like 0 equals, I'm going to put this in the front because it's the highest degree of t. So 0.0825t squared. Again, I should be drawing a little thing on that. Since we subtracted 4.85, we have negative 4.85t. And then we're going to still add 32 on the end, but there's no t next to it. So we're not going to really be concerning ourselves with this because it's on the far end, so we're not going to be putting it towards the top. But that's just organization. But yeah, this will make it easier because now we're going to do the quadratic formula. So in the quadratic formula, you have value of a, value of b, and a value of c. So here is the quadratic formula. So we have a, b, and c. So once you plug in to the quadratic formula these three things and you solve it, you're going to get two values, which are going to be our values of time, t1 and t2. So those two values I'll draw over here, so t1 and t2. Those two values, after you plug them in, I used a graphing calculator, are 7.57, and this is in seconds because it's a time, and 51.21 seconds. So from these two, we notice it wants the distance traveled from the two times. So basically we need to find the distance traveled between these two times. So we don't want it in terms of seconds, we want meters. So what we're going to do is we're going to take one of our equations here. I'm going to just use this equation because basically they're going to be traveling the same distance. So it doesn't really matter which equation you use. This one has like a bunch of different stuff in it, which will make it harder to calculate. So instead I'm going to be using the dog or puppy equation to calculate the distance between these two. So I'm going to do that by plugging both of these numbers in here, giving me a x1 and an x2. So the x1, basically for t, we're going to plug in this number, so 4.85 times 7.57. is equal to 36.731. I'm going to just do 73. And this is in meters because it's the distance. So that'll be the first point where they intersect. And then the second point where they intersect is going to be 51 seconds times 4.85 t. Or 4.85. T is the 51 seconds. So after we multiply those, we're going to get a value of 248. I'll just say 39 meters. So notice how it's saying distance traveled by the toy car from the time AV catches up with it the first time and when AV catches up with it the second time. So basically what's happening here is the puppy's going to pass the car because it's going to bite it, it's going to miss, it's going to pass the car, but then the car is going to zoom ahead past the puppy a second time. So that's going to be the second time where the puppy catches up to it. So basically, if the car is here and the puppy's here, it's going to catch up, the puppy's going to surpass it, and then the car is going to surpass it again. So we want to find the distance in between these two values. So we can do that by just taking x2 minus x1, which again is the change in x. So the change in x, which is going to end up being our final answer, will be, once we subtract these two values, 248.39 minus 36.73. Change in x will end up being, let me get a calculator out actually, 248.39 minus 36.73. We get a value of 211.66. I'll just say 211.7 because just to make it a little nicer of a number, and that's going to be in meters. So depending on how you ended up rounding it here, you could have a slightly different answer than me, but as long as it's around 211.7 meters, then you'll be fine. So this is going to be our final answer, saying the distance traveled. So next we're going to move on to the second part of the problem, which is saying below a certain minimum constant speed, AV would never catch the toy car. What would AV's minimum constant speed need to be to have exactly one attempt to catch it? So what I'm going to do here is I'm going to draw a graph again with x over here, meaning position or distance, and t over here. So now this is still assuming that the x reference for 0 is at where the puppy starts moving. So now what I'm going to do is I'm going to make two graphs. Again, I'm going to use blue for the car, because the car stays the same. And I'm going to use red for the dog. So this is going to be at 32 meters where it starts moving, and then it's going to be, I'm going to make a little bit better of a curve here. Yeah, that's good. Okay, so now we have a parabola representing this equation, basically, or the equation of the car. So now I'm going to redraw in our line we got from the last equation. So notice how this one crosses through it at 2 points. So this time it's saying we want a minimum constant speed to have exactly one attempt at catching it. So that means it's going to, there's going to be a lot of lines or lines representing the velocity of AV where it won't actually be able to catch the toy car. But there's going to be one that just touches it at one point, and that's what we want to find. So basically what we're going to do is we're going to recycle our equation that we found over here, except this time instead of putting 4.85 meters, we're going to just put velocity initial. So when we do that, we get an equation that looks like velocity initial times time, this is t, equals 32 plus 0.0825 t squared. So basically, in this equation, the 32 meters is still the same. The acceleration of the dog is still the same. Or, sorry, acceleration of the car is still the same. So that's why we're just maintaining this part of this equation, or this side of the equation. But this time, we don't know what the velocity is. We want a velocity initial, velocity final. The velocity is constant, so it doesn't matter. But we want a velocity minimum. So I'll just put min up here to remind us that we want a minimum velocity. And we only want one root. So in the last one, we had two roots, but we want one root. So to solve this, we're going to look at the quadratic formula. So in the quadratic formula, we notice that we have a plus and minus here. So the plus and minus is what controls whether we're going to have a two roots or one root. So what value would we have to add and subtract to get the exact same number? There's only one, and that is 0. So we want this to equal 0. So we're going to do exactly that. We're going to say b squared minus 4ac equals 0. So now, if we go back to our equation, I'm going to set this up a little bit differently by just putting the v on the other side so it looks like a quadratic. And I'm going to move this over in front because it has the highest degree of t's. So I'm going to say 0.0825t squared. And now we have minus VOT. I'm going to put a t here. Just a little loop to remind us. And 32. So this one will be A. This will be B. This will be C. So now we know what we're trying to solve for. We're trying to solve for B, or the velocity. So how do we get this all alone on one side? Well, what we can do first is we can square both sides, because there's a square root over all of this. And 0 squared is just 0. So we get b squared equals, b squared minus 4ac equals 0. And then what we're going to do is we're going to add 4ac on both sides. I'm going to just draw an arrow to represent adding it. And then we get b squared equals 4ac. Now, finally, what we're going to do is we're going to square root both sides to get rid of the squared here. We get a value of b equals the square root of 4ac. So, now we know our values of a and c. We have it in this equation right here. A is equal to 0.0825, and c is equal to 32. So I'm going to plug these back in, and we get b equals the square root of 4 times 0.0825. I'm going to extend this times 32. That was a little bit redundant. And when we use our calculator to multiply these numbers together, we're going to end up getting b equals the square root of 10.56. And the square root of 10.56 is approximately 3.25. So now if we go back to look at the question, it's saying what is the minimum constant speed need to be to have exactly one attempt at catching it. So basically we're going to say the velocity minimum is equal to, if we go back here, we see we get a value. We need to remember to include units on this though. So the units we're going to include are 3.25 given its velocity. We're going to be traveling a distance and a time, so we're going to have meters per second. This is an approximation. If you want to add the actual value, you can also say or 10.56 meters per second, and the 10.56 is square rooted. So those are our two values. So just to double check this, what I'm going to do is I'm going to show it on a graphing calculator. So the red represents the car. In this case, I guess I switched around colors, my bad. And the blue represents the dog in the first problem. So if we look at these 2 points, we see the y, again, will be position. The x will be time. A little bit confusing because usually in physics we use x for position, but that shouldn't matter. So in between these 2 points, there should be 211 roughly, and it looks like so. So we can confirm that our answer here is probably good. And then next, what we're going to do is we want to make sure that the root of 10.56x, or the equation, for the velocity, basically, of the dog is going to only have one root. And so we can check that by clicking here, and we can see, does it have a root? Yes. We can see it has a root, 19.695, but again, it's not asking where the root is, it's just saying the minimum constant speed, so we have velocity of 3.25. So to conclude, we have these two answers. I guess I rounded this one a bit less, but just 0.7. So basically we got this first answer by deriving an equation, and then making two equations, one for each object, and then we set the positions equal. Then we solved for the times, where they're going to have the same position. And then, after using those times, we re-plugged them back into the equation to get two positions, and then we subtracted them from each other, x2 minus x1, to get the change in x, which ended up being 211, which was exactly what the question was asking. And then, in this problem, we were asked to find the minimum constant speed, so we wanted to find where one root was, so we used the quadratic formula to find out where the root of this is equal to 0, and where that is equal to 0, that means it's plus or minus 0, so that means there's only going to be one root. So then we solved for a b value, which was the same as the initial velocity, which ended up being 3.25 meters per second. So that concludes this video. Thank you for watching. Yeah.